When we think of Tony Stark's arc reactor, we picture a glowing fist-sized device powering an advanced suit of armor and running for years without a single refuel. In Iron Man, it's described as a fusion-type power source, tiny, clean, and unbelievably powerful. Of course, it's fiction, but here's the interesting part. Real science is slowly moving in that direction. A real arc reactor would have to be a compact, insanely high energy density power system. In our universe, the closest candidate is nuclear fusion. Fusion works by heating light atomic nuclei like deuterium and tritium to over 100 million degrees Celsius and holding them there long enough for them to collide and fuse. When they do, they release enormous energy with no carbon emissions. And if the system fails, the reaction stops instantly. That's a safety feature fission reactors can't claim. But there's a catch. Holding plasma that hot is like trapping the sun in a bottle. The only way we have found to do it is to use incredibly strong magnetic fields. Plasma is a charged gas, so magnetic fields can hold it in place away from the walls. Devices like tokamaks and stellarators create these magnetic cages, and the real revolution here is high temperature superconductors. These materials carry electricity with zero resistance at cryogenic but not ultra cold temperatures. They can create magnetic fields of over 20 Tesla, which means we can shrink reactors to a fraction of their previous size. MIT's ARC concept, for example, would be half the size of ITER while still achieving the same magnetic confinement. So where are we now? We have multiple real-world paths moving forward. Compact tokamaks like Spark aim for net fusion by 2027. Spherical tokamaks like the ST40 pack plasma more tightly for better efficiency. Stellarators like Wendelstein 7X in Germany run for longer without disruptions. Field reversed configurations from companies like Helion aim to convert fusion energy directly into electricity, skipping turbines altogether. And magnetized target fusion from General Fusion uses liquid metal to compress the plasma. Each approach solves one piece of the puzzle, but none yet combines all the traits of a truly portable megawatt scale arc reactor. Now, if we designed one with today's tech, it would not fit in our chest. It would fill a small room. Picture a 2-meter cube weighing several tons. At its heart, a vacuum chamber lined with tungsten to survive intense heat and neutron blast. Around it, a tritium breeding blanket capturing energy and making fuel. Surrounding all of that, high-field superconducting coils wrapped in heavy neutron shielding. Fuel would be injected as gas or pellets, and power could be drawn as heat for turbines or directly as electricity, using techniques like Helion's pulsed induction. Sounds exciting, but here's why it's hard. We still have to hit the Lawson criterion, that balance of temperature, density, and confinement time. High field magnets must survive enormous forces. Neutrons threaten to damage and weaken materials. Tritium, which is radioactive, has to be handled safely without leaks. And all the while, we are trying to fit it into something small and manageable. Shrink the reactor too much, and most of your space disappears into shielding, magnets, and cooling, leaving very little room for plasma. Even so, fusion has major safety advantages. There is no runaway chain reaction. If the magnets fail, the plasma cools instantly. The main hazards are neutron radiation and tritium, which require careful shielding and handling. And in most countries, it will fall under nuclear safety laws. That means licensing, strict limits, and long-term safety demonstrations. So what's the roadmap? In the next 5 years, expect breakthroughs in high field magnets, tritium systems, and net gain plasma experiments. In 5 to 10 years, we could see experimental prototypes that combine these technologies and produce up to 10 megawatts of power. In a decade or more, we might see the first deployable power packs, still heavy, still bulky, but capable of delivering portable, clean energy anywhere it's needed. For now, the arc reactor remains an idea from science fiction. We can't build one the way Tony Stark did, but the principles behind it are no longer just fantasy. Fusion research is accelerating, superconductors are improving, and plasma control, once thought impossible, is becoming more stable. Each step is small, each step is incremental, yet together they are pointing in a clear direction toward a future where compact, powerful, and clean energy may be real. That is the story so far. Not a Hollywood invention, but a global scientific effort to turn limitless power from imagination into innovation.